Welcome friends to another session on mathematical modeling. In this session, we will discuss the car following model in detail. Traffic models part 2, car following models. Car following models of single lane traffic assume that there is a correlation between vehicles in a range of inter-vehicle spacing from 0 to about 100 to 125 meters and provide an explicit form of this coupling. The modeling assumes that the driver in a following vehicle is an active and predictable control element in the driver vehicle road system. These tasks are termed psychomotor skills or perpetual motor skills because they require a continued motor response to a continuous series of stimuli. The relatively simple and common driving task of one vehicle following another on a straight roadway where there is no passing, that is neglecting all other subsidiary tasks such as steering, routing, etc., can be categorized in three specific subtasks. First one is perception. The driver collects relevant information mainly through the visual channel. This information arises primarily from the motion of the lead vehicle and the driver's vehicle. Some of the more obvious information elements, only part of which a driver is sensitive to, are vehicle speeds, acceleration and higher derivatives, example jerks, inter-vehicle spacing, relative speeds, rate of closure and functions of these variables, example a collision time. Second one, decision making. A driver interprets the information obtained by sampling and integrates it over time in order to provide adequate updation of inputs. Interpreting the information is carried out within the framework of a knowledge of vehicle characteristics or class of characteristics and from the driver's vast repertoire of driving experience. The integration of current information and catalogued knowledge allows for the development of driving strategies which become automatic and from which evolve driving skills. Third one, the skilled driver can execute control commands with dexterity, smoothness and coordination, constantly relying on feedback from his own responses which are superimposed on the dynamics of the system counterparts, that is the lead vehicle and roadway. It is not clear how driver carries out these functions in detail. The millions of miles that are driven each year attest to the fact that with no or little training, drivers successfully solve multitude of complex driving tasks. Many of the fundamental questions related to driving tasks lie in the area of human factors and the study of how human skill is related to information processes. The process of comparing the inputs of a human operator to that of the operator's outputs using operational analysis was done. These attempts to determine the mathematical expressions linking input and output have met with limited success. One of the primary difficulties is that the operator, that is the driver, has no transfer function. The driver is a different mechanism under different conditions. During the course of studies like these, a number of useful concepts were developed. For example, reaction times were looked upon as characteristics of individuals rather than functional characteristics of the task itself. In addition, by introducing the concept of information, it has proved possible to parallel reaction time with the rate of coping with information. Knowledge of human performance and the rates of handling information made it possible to design the response characteristics of the machine for maximum compatibility of what really is an operator machine system. The very concept of keeping an operator as a transfer function implies partly that the operator acts in some continuous manner. There is some evidence that this is not completely correct and that the operator acts in a discontinuous way. There is a period of time during which the operator, having made a decision to react in an irreversible state, and that the response must follow at an appropriate time which later is consistent with the task. The concept of human behavior is discontinuous in carrying out tasks, and the sequential responses are correlated in such a way that the response time to a second stimulus is affected significantly by the separation of the two stimuli. Inertia, both in the operator and the machine, creates an appearance of smoothness and continuity to the control element. In car following, inertia also provides direct feedback data to the operator which is proportional to the acceleration of the vehicle. Inertia also has a smoothing effect on the performance requirements of the operator, since the large masses and limited output of drivetrains eliminate high frequency components of the task. Car following models have not explicitly attempted to take all of these factors into account. The approach that is used assumes that a stimulus response relationship exists that describe the control process of a driver vehicle unit. The stimulus response equation expresses the concept that a driver of a vehicle responds to a given stimulus according to the relation response is equal to lambda into stimulus, where lambda is a proportionality factor which equates the stimulus function to the response or control function. The stimulus function is composed of many factors: speed, relative speed, intervehicle spacing, accelerations, vehicle performance, driver thresholds, etc. What is generally assumed in a car following modeling is that a driver attempts to keep up with the vehicle ahead and avoid collisions. These two elements can be accomplished if the driver maintains a small average relative speed u relative over short time periods, say delta t, that is ul minus uf is equal to u relative, which is equal to 1 by delta t integral t minus delta t by 2 to t plus delta t by 2 u relative of t dt is kept small. This ensures that collision times T c is equal to S t by u relative are kept large, and intervehicle spacing would not appreciably increase during the time period delta t. The duration of the delta t will depend in part on alertness, ability to estimate quantities such as spacing, relative speed, and the level of information required for the driver to assess the situation to a tolerable probability level, and can be expressed as a function of the perception time. Because of the role relative speed plays in maintaining relatively large collision times and in preventing a lead vehicle from drifting away, it is assumed as a first approximation that the argument of the stimulus function is the relative speed. From the discussion we have done on the driver characteristics, relative speed should be integrated over time to reflect the recent time history of events, that is, the stimulus function should have the form like that of equation 2 and be generalized so that the stimulus at a given time depends on the weighted sum of all earlier values of the relative speed, that is ul minus uf is equal to u relative, which is equal to 1 by delta t into integral t minus delta t by 2 to t plus delta t by 2 sigma of t minus t dash u relative of t dash dt dash, where sigma t is a weighting function which reflects a driver's estimation, evaluation, and processing of earlier information. The driver weighs past and present information and responds at some future time. The consequence of using a number of specific weighing functions has been examined, and spectral analysis approach has been used to derive a weighting function directly from car following data. The general features of a weighting function can be seen from figure 1. This figure shows the schematic diagram of relative speed stimulus and a weighting function versus time. What has happened a number of seconds in the past is not highly relevant to a driver now, and for a short time a driver cannot readily evaluate the information available to him. One approach is to assume that sigma t is equal to delta of t minus capital T, where delta of t minus t is equal to 0 for t not equal to capital T, and delta t minus t is equal to 1 for t is equal to capital T. And we have integral 0 to infinity delta t minus t is equal to 1. For this case, our stimulus function becomes stimulus of t is equal to ul of t minus uf of t minus t, which corresponds to a simple constant response time capital T for a driver vehicle unit. In the general case of sigma t, there is an average response time t bar given by t bar of t is equal to integral 0 to t dash sigma t dash dt dash. The main effect of such a response time or delay is that driver is responding at all times to a stimulus. The driver is observing the stimulus and determining a response that will be made sometime in the future. By delaying the response, the driver obtains advanced information. For redundant stimuli, there is little need to delay response apart from the physical execution of the response. Redundancy alone can provide advanced information, and for such cases response times are shorter. The response function is taken as the acceleration of the following vehicle because the driver has control of this quantity through the accelerator and brake pedals, and also because a driver obtains direct feedback of this variable through inertial forces. That is, response t is equal to AFT, which is equal to XF double dot t, where XFT denotes the longitudinal position along the roadway of the fth vehicle at time t. Combining equations 8 and 10 into equation 1, the stimulus response equation becomes XF double dot t is equal to lambda into XL dot t minus XF dot t minus t, or equivalently XF double dot t plus t is equal to lambda into XL dot t minus XF dot t. Equation 12 is a first approximation to the stimulus response equation of the car following, and as such it is a grossly simplified description of a complex phenomenon. The generalization of car following in a conventional control theory block diagram is shown in figure 2. In the same format, the linear car following model presented in equation 12 is shown in figure 3. In this figure, the driver is represented by a time delay or a gain factor. A more complete representation of car following includes a set of equations that would model the dynamical properties of the vehicle and the roadway characteristics. It would also include the physiological and psychological properties of the drivers, as well as couplings between vehicles other than the forward nearest neighbors and other driving tasks such as lateral control, the state of traffic and emergency conditions. For example, the vehicle performance undoubtedly alters driver behavior and plays an important role in real traffic, where mixed traffic represents a wide performance distribution and where appropriate responses cannot always be physically achieved by a subset of vehicles comprising the traffic stream. Now, we will move on to the stability analysis. In this section, we address the stability of the linear car following equation 12 with respect to disturbances. Two particular types of stabilities are examined: local stability and asymptotic stability. Local stability is concerned with the response of the following vehicle to a fluctuation in the motion of the vehicle directly in front of it. That is, it is concerned with the localized behavior between pairs of vehicles. Asymptotic stability is concerned with the manner in which a fluctuation in the motion of any vehicle, say the lead vehicle of a platoon, is propagated through a line of vehicles. The analysis develops criteria which characterize the types of possible motion allowed by the model. For a given range of model parameters, the analysis determines if the traffic stream as described by the model is stable or not. That is, whether disturbances are damped, bounded or unbounded. This is an important determination with respect to understanding the applicability of the modeling. It identifies several characteristics with respect to single lane traffic flow, safety and model validity. If the model is realistic, this range should be consistent with measured values of these parameters in any applicable situation where disturbances are known to be stable. It should also be consistent with the fact that following a vehicle is an extremely common experience and is generally stable. Let us see local stability. In this analysis, the linear car following equation, that is equation 12, is assumed. As before, the position of the lead vehicle and the following vehicle at a time t are denoted by XLT and XFT respectively. Rescaling time in units of the response time using the transformation small t is equal to tau into capital T, the equation 12 simplifies XF double dot tau plus 1 is equal to C into XL dot tau minus XF dot tau, where capital C is lambda into capital T. The conditions for the local behavior of the following vehicle can be solved by solving equation 13 by the method of Laplace transforms. For example, for the case where the lead and following vehicles are initially moving with a constant speed u, the solution for the speed of the following vehicle was given by Chow, where v denotes the integral part of t by capital T. The complex form of the solution makes it difficult to describe various physical properties. Xn dot t is equal to u plus summation sigma is equal to 0 to v minus n integral n plus sigma t to small t minus 1 raised to sigma lambda raised to n plus sigma into norm tau minus n plus sigma into t raised to n plus sigma minus 1 divided by n minus 1 factorial into sigma factorial into u dot t minus tau minus u dt. However, the general behavior of the following vehicle's motion can be characterized by considering a specific set of initial conditions. Without loss of generality, initial conditions are assumed so that both vehicles are moving with a constant speed u. Then using a moving coordinate system z of t for both lead and following vehicles, the formal solution for the acceleration of the following vehicle is given by L inverse of c into c plus s e raised to s inverse into s, where L inverse denotes the inverse Laplace transform. The character of the above inverse Laplace transform is determined by the singularities of the factor c plus s into e raised to s inverse, since c s square z L s is a regular function. These singularities in the finite plane are the simple poles of the roots of the equation c plus s e raised to s is equal to 0. Similarly, the solutions for vehicle speed and intervehicle spacing can be obtained. Again, the behavior of the intervehicle spacing is dictated by the roots of equation 16. Even for small t, the character of the solution depends on the pole with the largest real part, say s dot is equal to a dot plus I b dot, since all other poles have considerably large negative real parts, so that their contributions are heavily damped. Hence, the character of inverse Laplace transform has the form e raised to a dot t into e raised to I b dot t. For different values of c, the pole with the largest real part generates 4 distinct cases. First one, if c is less than or equal to e raised to minus 1, that is approximately 0.368, then a dot is less than or equal to 0 and b dot is equal to 0, and the motion is non-oscillatory and exponentially damped. Second case, if e raised to minus 1 is less than or equal to c less than or equal to pi by 2, then a dot is less than 0 and b dot is greater than 0, and the motion is oscillatory with exponential damping. Third case, if c is equal to pi by 2, then a dot is equal to 0, b dot is greater than 0, and the motion is oscillatory with constant amplitude. And the fourth case, if c is greater than pi by 2, then a dot is greater than 0 and b dot is greater than 0, and the motion is oscillatory with increasing amplitude. These cases establishes a criteria for the numerical values of c which characterize the motion of the following vehicle. In particular, it demonstrates that in order for the following vehicle not to overcompensate to a fluctuation, it is necessary that c is less than 1 by e. For values of c that are somewhat greater, oscillations occur but are heavily damped and thus insignificant. Damping occurs to some extent as long as c is less than pi by 2. These results concerning the oscillatory and non-oscillatory behavior apply to the speed and acceleration of the following vehicle as well as to the intervehicle spacing. Thus, for example, if c is less than 1 by e, the intervehicle spacing changes in a non-oscillatory manner by the amount delta s, where delta s is equal to 1 by lambda times v minus u, when the speeds of the vehicle pair changes from u to v. An important case is when the lead vehicle stops, then the final speed v is 0 and the total change in intervehicle spacing is minus u by lambda. In order for a following vehicle to avoid a collision from initiation of a fluctuation in a lead vehicle's speed, the intervehicle spacing should be at least as large as u by lambda. On the other hand, in the interests of traffic flow, the intervehicle spacing should be small by having lambda as large as possible and yet within the stable limit. Ideally, the best choice of lambda is e t raised to minus 1. Because the initial and final speeds for both vehicles are u and v respectively, we have integral 0 to infinity x f double dot t of t plus capital T dt is equal to v minus u, and from equation 12 we have lambda into integral 0 to infinity x l dot t minus x f dot t dt is equal to delta s, or delta s is equal to integral 0 to infinity x l dot t minus x f dot t dt, which is equal to v minus u by lambda. It is interesting to note that in solving the linear car following equation for two vehicles, estimates for the local stability condition were first obtained using an analog computer for different values of c, which differentiate the various type of motion. Figure 4 illustrates the solutions for c equal to e raised to minus 1, where the lead vehicle reduces its speed and then accelerates back to its original speed. Since c has a value for the locally stable limit, the acceleration and speed of the following vehicle as well as the intervehicle spacing between the two vehicles are non-oscillatory. So, in this figure you can see vehicle 2 follows vehicle 1, that is a lead car, with a time lag t is equal to 1.5 seconds and a value of c is equal to e raised to minus 1, which is approximately equal to 0.368, that is the limiting value for local stability. The initial velocity of each vehicle is u. In figure 5, the intervehicle spacing is shown for 4 other values of c for the same fluctuation of the lead vehicle as shown in figure 4. The values of c range over the cases of oscillatory motion where the amplitude is damped, undamped and of increasing amplitude. So, in this figure note that changes in car spacing from an original constant spacing between two cars for the noted values of c. The acceleration profile of the lead car is the same as that shown in figure 4. For the values of c is equal to 0.5 and 0.8, the spacing is oscillatory and heavily damped. For c is equal to 1.57, which is approximately equal to pi by 2, the spacing oscillates with constant amplitude. For c is equal to 1.6, the motion is oscillatory with increasing amplitude. Local stability with other controls. Qualitative arguments can be given of a driver's lack of sensitivity to variation in relative acceleration or higher derivatives of intervehicle spacings because of the ability to make estimates of such quantities. It is of interest to determine whether a control centered around such derivatives would be locally stable. Consider the car following equation of the form x f double dot of tau plus 1 is equal to c into d raised to m by d t raised to m x l tau minus x f tau for m equal to 0, 1, 2, 3 etc. That is a control where the acceleration of the following vehicle is proportional to the mth derivative of the intervehicle spacing. For m equal to 1, we obtain the linear car following equation. Using the identical analysis for any m, the equation whose roots determine the character of the motion, which results from equation 20, is c plus s raised to m e raised to s is equal to 0. None of these roots lie on the negative real axis when m is even. Therefore, local stability is possible only for odd values of the mth derivative of spacing. Relative speed, the first derivative of relative acceleration, say m equal to 3 etc. Note that this result indicates that an acceleration response directly proportional to intervehicle spacing stimulus is unstable. Before we conclude, let us summarize what we have learned in this session. We started the session with the model development. We have discussed in detail the parameters considered in the model. We have also done the stability analysis, in which the local stability was discussed in detail. We will continue with the asymptotic stability in the next session. These are some exercise problems based on the topic in the session. First problem, suppose the velocity field is given by u of x t is equal to 30x plus 30L by 15t plus L. Determine the motion of a car which starts at x equal to L by 2 at t equal to 0. Show that u of x t is constant along straight lines in the x t plane, but the car does not move at a constant velocity. Second problem, suppose that a velocity field u of x t is known. What mathematical problem needs to be solved in order to determine the position of a car at later times which starts at t equal to 0 at x equal to L? Third problem, if a 10 meter per hour cars are one car length behind each other, then what is the density of traffic? Assume that the average length of a car is approximately 16 feet or 5 meters. Fourth problem, suppose that at position x naught the traffic flow is known q x naught t and varies with time. Calculate the number of cars that passes x naught between t equal to 0 and t equal to t naught. Here are some books for further reading. First one, Notes on Traffic Flow by Childress Stephen. Second one, Comparison of Car Following Models by Alstom, Johan Janssen and Andreas Tapani in 2004. Third one, Modules in Applied Mathematics Volume 1, Differential Equation Models by editors Martin Braun, C. S. Coleman, D. A. Drew, Springer-Verlag 1982. Fourth one, Modules in Applied Mathematics Volume 3, Discrete and System Models by W. F. Lucas, F. S. Roberts, R. M. Thrall, Springer-Verlag 1982. With this, we come to an end of this session. We will continue with the asymptotic stability of car following models in the next session. Till then, goodbye.